Good morning, my name is Mengying Peng. I'm currently a PhD student from Ghent University, and today I'd like to present how the in-situ absorption influences the temperature profile in soda lamp silica glazing based on both experimental and numerical studies. In the modern society, glazing is increasingly regarded as a load-bearing material in the buildings. However, the fair performance of glazing hasn't been fully understood yet, and a key distinction between glazing and the other common building materials with regard to the fair performance is related to the existence of the in-situ absorption. Therefore, this study provides preliminary investigations into the effects of in-situ absorption based on both numerical and experimental studies. A heat transfer model is applied in this study to investigate the influence of in-situ absorption. The glazing element is divided into slices. On exposed and unexposed surface, both convection and radiation are considered. As is known, glazing is a transparent material. Therefore, when it's exposed to a radiant heat, part of the radiation will be transmitted through the glazing thicknesses. And according to a previous study, the interior part of the glazing actually absorbs part of the radiation from the transmitted thermal radiation. Therefore, to investigate the effect of the in-situ absorption, three different situations are considered for the interior part of glazing elements. In FDM1, the in-situ absorption is not considered. In FDM2, the in-situ absorption is considered from the total incident radiation, and therefore is constant in each slice. In FDM3, the in-situ absorption is considered from the gained incident radiation, and thus is gradually reduced with distance from the exposed glazing surface. The figures here present the results for the temperature and the relative temperature difference through glazing thicknesses at various times. From the results, we can clearly see that there is an increase in the glazing temperature after considering the in-situ absorption, which is up to around 10%. However, the difference between FDM2 and FDM3 is very limited, which is less than 1%. Then I'd like to talk about the experimental part. During our experiment, a radiant panel is placed parallel facing downwards to irradiate the glazing sample. Each glazing sample has a thickness of 7.8 mm and is placed 42 cm from the radiant panel. The intensity of the radiant panel is 60%, which can generate a heat flux of 25 kW per square meter on the front glazing surface. The heat flux measurement on the front glazing surface is denoted as HF1. When the heat flux gauge is placed behind the glazing sample, the heat flux measurement is denoted as HF2 when the glazing sample is not present, and as HF3 with the glazing sample in place. In total, 3 different experiments are conducted in this study. The experiment 1 is intended to find the steady-state threshold, and 4 thermocouples are affixed with the glazing sample by applying the aluminum tape on both sides of the thermocouples. The experiment 2 is manually attached experiment. The experiment setup is the same as the experiment 1 during the heating phase. However, in the cooling phase, after shutting down the panel, an insulation board is placed between the radiant panel and the glazing sample. And at the same time, 2 thermocouples are manually attached to the glazing sample. The experiment 3 is the black paint experiment. All the surfaces of the glazing sample are sprayed black by using a fail-resistant paint, and 2 other additional thermocouples are attached to the glazing sample. Firstly, I'd like to show the results of experiment 1. From the results, we can see the steady state is achieved at around 30 minutes. The front glazing surface temperature can reach at around 300 Celsius, while the back glazing surface temperature can reach at around 285 Celsius. Furthermore, the ethylene drop cannot be observed in the backside thermocouples, while ethylene drop can be observed in the backside thermocouples when the thermocouples are only covered by the aluminum tape on one side. This is because when applying the aluminum tape on both sides of the thermocouples, it can help to block the thermocouples on the unexposed side from the direct front radiation. Then, I'd like to show the results of experiment 2. As mentioned before, an insulation board is placed between the radiant panel and the glazing sample. Therefore, these two manually attached thermocouples are expected to return the temperature measurements accurately. So, by comparing the temperature measurement results of the other thermocouples with these two manually thermocouples, the accuracy of the other thermocouples measurements can be confirmed in the cooling phase. So from the results, we can see the temperature curves of these two manually attached thermocouples are similar to the other thermocouples. Therefore, the experimental results in the cooling phase can be confirmed. Then the experimental results are compared with the simulation results. From the graph, we can see both of them indicate the steady state is achieved at around 30 minutes, and both of them can indicate there is a temperature difference of around 25 Celsius between the front glazing surface temperature and the back glazing surface temperature. However, there is a large difference up to 70 Celsius when comparing the experimental results with the simulation results. And this may be attributed to the thermocouples measurements or the simulation input. Finally, I'd like to show the results of experiment 3. From the graph, we can see the experimental results of experiment 3 is much higher compared with the other experimental results. And this is because after the glazing sample is sprayed black, the transmitted part is confirmed to be very limited, and therefore the absorptance is much higher. So in our simulation input, we assume the absorptance is equal to 1. Despite this simplified scenario, there is still a clear difference between the simulation model and the experimental results. And this indicates there may be an issue with our traditional application of thermocouples on the glazing surface for the temperature measurements. And also, the model input need to be further checked. As mentioned in the experimental setup, the heat flux measurements are also conducted in this study. From the results, we can see the heat flux actually increases before the final stabilizing, and this is attributed to the protective glass of the radiant panel. The protective glass actually absorbs the heat from the radiant panel, and as it heats up, it starts to emit its own thermal radiation and contributes to the heat flux. And the increased stage of the heat flux is also considered in our simulation input. The emissivity and transmissivity can also be calculated based on the experimental results. After shutting down the panel, an inflection point can be observed on the heat flux curve, and this is denoted as the emission energy from the heated glazing sample. Then the emissivity can be calculated based on this value and the back glazing surface temperature at this inflection point, and of course also by considering the view factor, as there is a distance between the glazing sample and the heat flux gauge. Then the transmissivity can also be calculated by considering the transparency of the glazing sample and this emitted energy from the heated glazing sample. To figure out which parameter has the largest influence on the glazing surface temperature, a series of parameter studies have been conducted, and this is done by adjusting the value of the parameter and comparing the temperature results with the temperature results from experiment 1. And from the results, we can see the absorptivity and heat flux have the largest influence, while the emissivity and specific heat have a small influence, and the influence of conductivity and convective coefficient is very limited. So a re-evaluation of these key parameters is in process. In conclusion, the in-cyclus absorption has a significant influence on the glazing temperature increase. And based on the parameter study, the most influential parameters for glazing surface temperature are absorptivity and heat flux. And a temperature difference up to 70 Celsius degree can be observed when comparing the experimental results with the simulation results. And this might be attributed to the thermocouple measurements and the model inputs. Therefore, further investigations are suggested to be conducted on the thermocouple measurements by considering the direct front radiation and the thermal resistant contact between the thermocouples and the glazing sample. And an appropriate model input needs to be further confirmed. So thank you for your attention again. If you have any further questions, feel free to contact me.